Hey, how's it going? We're doing Facebook Hacker Cup, round one. Let's see. 3 problems. Oh, the last problem's about a blockchain. Okay. I guess I don't need D. A1, A2, A3. Okay, cool. I think I should do A first for sure because 3 times as much penalty. So let's go. F1X. Okay, it's F1X because the problem setter goes by Lone Fox on Code Forces. Okay. Okay, this is a fairly straightforward DP. Are they even greedy? Yeah, actually, it should just the F's don't matter. Yeah. Let GS be the sum of FW overall substrings. Okay, yeah, it's just the F's don't matter. It's purely just the number of X's and O's. And what's this one? Especially through a string U of length K. Oh, wow. What? Okay, that is kind of crazy. Okay, I guess we'll start with A1. So how do you solve a string? It's just count how many times we go from X to O to X. So this is 0, 1, this is 0, 2, 1, 2, 3, 4, 5, 6. Okay, yeah. Because that's how many times you have to switch. Yeah. Okay. So I'm going to just look on A1 and let's input it's N in the string. Yes, no, we'll just call it W like we did in the problem. Okay, so otherwise, okay. No, not A1. 0, 1, yep, that looks good. I'm gonna remove a.tc before I mess up. That's a previous contest we're doing. Okay. Put. It's good. And Oh, I don't have to do this. I can just do this. Download directly. Okay, and we'll do output, and we'll do I mean, seems reasonable. Okay, so that's it for that. Alright, now that we know how to do A1, how are we going to do A2? 24th place, that's fine. Okay. A1 to A2, that's this one. So given a certain string, we're essentially get a little bit of light here. Okay, okay. All right, so given a, oh, this sunlight makes me look really blue. Given a substring, so if it doesn't have any x's or o's, it's 1. Well, it's 0 actually. It's actually 0. If it only has one type of x or o, it's also 0. It's just the number of changes, which is kind of weird. So for any character, oh yeah, for any character, how much does this count? Well, it has to be different from the last x or o, and that x or o has to be included. So, okay, I think that's right, actually. If wi equals x or wi equals o, and if wi not equal w previous, now we have total plus equals basically any string that contains I and contains previous. That means we have previous plus 1 choices for the left endpoint, and for the right endpoint we have n minus I. Is that it? Maybe that's it. It looks good. Okay. Yeah. Okay, cool. Let's go over it. Let's output. Wrong answer. Oh, we want modulo. Oh, wow. I didn't even notice that we want modulo. Why do we want modulo? We can just fit into it. Okay, well. What is that? No. Oh, it's because this is broken. Is that why? Okay, no. Or I can just respawn. So funny. Okay, now we're, yep. And that's different. Yeah, it's different. Okay. Cool. I don't need this. I mean, I have to click this just to get this. Output. Okay, seems good. Okay, so now that we know how this works, I think A3 should be relatively easy. If you add a character to the end, then basically, yeah, basically we're taking the sum of all these characters. Now, how do you add a character to the end? Well, all of these n minus i's increase by 1, so you need to know the sum of previous plus 1. You know the sum of previous plus 1, good. Oops. B isn't too hard. Might be worth doing B instead of B3. Sure yet. What is it? Okay, so 2 ops at the end. Yeah, add something to the end. Add something to end is, so first of all, for existing, you just add to the end. First you do plus equals the sum of, and then if this is different from the previous thing, we need to know where the previous thing is. We need to know what the previous thing is. We need to know what the previous value is. Previous values, and then we just add this, we add this to the sum. God, it's like it's a bunch of math. Maybe B is the play. 7 minutes. Yeah, I think B is the play. Alright. Cool. This is kind of a weird problem. Wait. Wait. Can you just... If they're both at least 3, you can just only set... Wait, what? Can't you just set the top left and the top right to A and B? Oh, everything has to be at least 1. Oh, everything has to be at least 1. Okay, but that doesn't really matter. Wait, yeah, that's super easy. What the heck? Okay, let's do it. Am I understanding this right? So, if min A B is less than... Because it has to be at least that much, yeah. Otherwise... Oh, oops. That's a little bit annoying. Possible, and then yeah, what we're doing is... I really didn't need to make this array, but it's fine. Oh, that's the right file. Cool. Looks good. Why do I have to do this? I'm just forced to download both. Okay, let's do that. Let's do that. Okay, that problem was surprisingly easy. I imagine a lot of people are just doing A3. Yep, looks good. No one on A3 yet. And it's at least 2, right? 2 by 2. Yeah, seems fine. Okay. Not gonna click on that. It's just bait. It's tree. AI, BI, C. Okay, tree. No. Okay, so it's a min. Yep. Okay, so okay, so if you block equal 20. Oh, okay. I think I see what's going on. Is this centroid decomposition? Do we have to do it? I have a rough idea how to do this. I think A3 is probably simpler. Just work up equations. Okay, yeah, so let's do A3. Let's do it. The idea is, so what do we have? We have first, we have first char, we have last char, we have count, we have sum of P1. Is that it? So basically we need a new thing. Let's add to the end. We're gonna add sum of P1, right? And we also need n. We're gonna add sum of P1. We're also gonna have our total. Okay, so we add a new thing to the end. We add sum of P1. We're gonna add sum of P1, yeah. And just update all of these appropriately. And if we're adding an X or an O, we just compare it with last. If last is different, then we're gonna add one more thing. Right, yeah, we'll update that. Yep. And then how we duplicate. So duplicate. Ooh, let's update all these. So duplicate is, these are fine, these don't change. Well, this changes. Count doubles. Count doesn't exactly double. Count, what does count do? Means our last is -1, which is nice. So what happens to count? If all these duplicate and they get n added, the one thing is this one may be the same. All these duplicate, they get n added to them. So n. Okay, so we do. We need the sum of n minus I as well. Ooh, it's kind of annoying. These are mods. Oh, they're mods? They have remoddeds, yeah. I really don't need K. It's kind of useless. Okay. So what happens when you add to that? We total plus equals the sum of P1 because, yep, that happens. Does anything else automatically happen? Sum ni plus equals count. Yes. Sum P1 doesn't change. Yeah, and now if it's X or if it's O. First of all, if I didn't have N here. Then first char equals N, no, first plus N. Last char is char. We need to compare it first. If last char not empty and last char. Now we have a situation. Now this is a new one. This is a new one. What do we do with a new one? Oh, this is so heavy on the casework. Maybe we should have done C. Okay, well, I'm already deep into this. Let's just keep going. Last char is not empty and char. Then we update last char. We update count. We update sum P1. Times 1. Because, you know, ni is just 1. N minus I is 1, so we're just doing that. N plus plus. There's also N. What happened to N? I still need N. What did I do? I'm going to scratch that one. Total plus equals last one. Sum P1 plus equals N plus 1 because, yeah. Sum Ni plus equals 1 basically. Count plus plus. Also last is going to become N, last char is going to become char. That seems like that's it. Okay. Now we're duplicating the string. Oof. This is kind of annoying. So now we have to handle this. Also first, either they're both empty or they're neither is empty. If they're both empty, what happens? These don't change, these don't change, that doesn't change, and doubles. 2, and that's it. I think that's it. Count doesn't change, count 0, sum 0, sum 0, total 0. Okay, yeah. Okay, so now they exist. First doesn't change, last doesn't change. Count doubles and doubles. What happens to these sums? So total plus equals, so now we have all these new things. Now we have all these new things, which are, it's just so now we're going to add what are we doing here? We have so for all the already existing ones, they're n minus I, just added an n. So we're doing n times sum p1, right? Now for the new guys, the n minus 1, the n minus I stayed the same, but their previous plus 1 added n. The previous plus 1 just added n. Okay? And now there's one special case, which is if first char equals last char, then we're not counting that. How did we do that anyway? I think we're already not counting it because I think it's actually this case where we need to count. There's actually two cases. In this case, we need to count it, so we need to add times n minus n plus first, or just n minus first? So sum p1 adds p1 plus n times count, sum ni plus equals they're equal, we just subtract this last thing. So n plus first plus 1. N plus first plus 1. We don't want that one. That's correct. Okay, so we also want it's last plus 1. Last plus 1. We don't want that. Is that everything? I want to double check the logic, but maybe if we just get this right. How is that possible? Okay, we're a little bit off. Just do this. Yep. Okay, so that's the first one we got. Unfortunately, it's these big ones. What should we do? Oh, we actually get this case wrong. So the nice thing about this is that any test case for A2 is also a test case for A3. Yes, so we can just do this too. And I mean, that's where this came from, I guess. Ah, okay, so 3xx, 3xx, okay, 1, 2, xo. So xx, let's do xx. So xx should be 4, and we get 5. So why do we get that? Oh, I think we want to do this regardless. What am I doing? Seven? That's not what we want at all. 7? Some people. What is this? No, that is super wrong. Four? No, around 22. Okay, but we're still getting. All right, let me just double check all the logic here. Okay. I think we should swap these. Because total plus equals sum p1, because all the p1 times that, all these increase by 1. Sum ni plus equals count. Yeah. Yeah. It's not equals the last char. Total plus equals last plus 1. Yeah. Yeah. Sum ni plus plus. Yeah. Count plus plus last equals n. So am I getting it wrong when there's A's, when there's F's involved? What is happening? Why can't I make a case that? Okay, I'm just gonna do this. Let's do this real fast. Three. So final one is OOX. Because last is set to it regardless. Is that what it is? Okay, now we pass. Now here's the part we pass A2. This needs to update last. Oh. Is that what it is? Oh, we need to do that regardless. Okay. Whoa. Let's save the progress. Let's ignore these two because everything else is reasonably small. Nothing is too big. All right, so we pass on A2, and now we fill. Sorry, not this. We fill this. Now, how can we? What could be wrong here? Let's check this line. So this seems like it's all correct, right? I mean, it has to be passing that. Although I don't use first. Yes. Sum of P1. Yep. Sum of NI adds count. Sure, that makes sense. As long as char is not equal to last char. Let's try this char. plus equals n. First row is empty, then none of these, nothing happens to any of these except, yeah. Total plus equals total plus, so yep. And then all of their n's get bought, so n times some p1, and all of their I guess this guy had a -1. So this guy had a -1, so oh, that's not really right. Oh. Yeah, the first one gets messed up. Is that what happens? So the first one gets messed up. N minus first. Because this guy, basically this guy is alright, collect all of them. Is this good now? Alright, so n possible total plus n times on p1. No. Oh no, count. Count. Oh no, this is bad. Okay, so wait. What? Oh, it's n. Wait, oh dear. This makes sense to me now. Now I get everything but the last, which is not fun. Let's do this again. Let's do this. Let's make this into A3 slow. O dot O dot. Okay. X dot F dot. Oh, I see. So why is that? There's something that's not getting clear out of here. Just about all the state. Some P's and right? First, last char. Count n, some P1, some Ni. Oh, total. We double it. So count 2, n is 2, some P1. Some Ni is 2? I guess it is. Do it again. Some P1. How did some P1 become? Oh. Oh, but some Ni is already wrong. Like some P1 is already wrong. Oh, because it's last is not necessarily one of them, which is weird. Plus n times, which is 4 times sum of P1. Sum P1 plus equals sum P1 plus n times count. That is. What is going on? Oh, this is really confusing. Sum P1 plus. That seems sensible. Oh, why did count increase? Oh. Is that what it is? Let's make the test stronger. Kind of expect something to be done. I don't think C's that hard. Yeah, something's done. Okay. All right, let's finish this. Let's do C. I forgot to do this. There's way too many files. Way too many files here. Let's stop this. Do this. That was a messy bug. All right, so this, I think it's pretty simple. Basically, you can get the initial, and then you can get the initial is just go through the sorted edges, and when it, yeah, you just union fine. That's fine. Yep, okay, so I think I know what to do here. Do I need center decomposition? I think you want center decomposition because you don't know otherwise. This is a good candidate for edge center decomposition. The reason is, yeah, the edge version is pretty simple. You just have two halves and you, yeah. I think that's right. Okay, so how's it put? Inputs. I think this is what we want. Just like this. All right, and now there's no K. Maybe I can just do this. Modent. It's kind of hilarious that it's 64. I don't have K. Weight depth is not a thing. There's like weight min. It's kind of a thing. Okay, so add empty edge. Empty edge. Okay, and there's also there is some level of looks good. Wait, what am I doing? No, saturate is not what you want because saturate is not what you want because if you oh wait, the center is it what you want? It's like I think I still want center decomposition. Okay, so this is a special edge, and then we're gonna. So there's this. This will be solved later. There's this among itself. No, sorry, there's this among itself that will also be solved later. There's this cross into this. Is that right? Maybe that's right. So yeah, maybe I didn't need the edge version. Okay, I think this is pretty reasonable. What we really want is the count. do this. I don't want indices anywhere. Oh, I actually don't want to make this. Oh, I see why it does that. Because you could allow weights that are... I don't know, I don't like that. We'll do this later. Okay, so... No, that's not how I want frequency to work. It does, is it? That's how I want it to work. Okay, so now it works, and this is void. So we got monads, we got equivalents. These can be constant references. It's make a big difference, but as well just not. Node is this one's for it. What do you lose if you cut this node? Yeah, we need to save answers. So let's go here. It's cool. Answers. That's not really. Wait, am I doing this right? So it should actually turn across. This switches so. This is what, so yeah, so okay, so we're back to what do we lose? We lose this and this. What do we lose? We lose Is this done? Does this work? That would be surprising. Okay, let's just do this. So we probably didn't allocate. Oh, no, not answers node. Again, not answers node. It is... Oh. Okay, these actually aren't too bad. So we have 10, we have 1, we have 5. There's everything. 10, 1, 5, 1, 1, 5. 10, 1, 5, 1, 1, 5. 23, yep, that makes sense. If we remove this, step up 1, we lose 16. If we remove this, we lose 0. Why do we lose 0? No, we lose something. For sure we lose something. We're doing 5, 1. Oh man. So I think we end up like this. 2. Shouldn't it be? $20 to 5 is a 1, right? Oh, we're not counting this thing because it doesn't exist. So above, there's a 20. This is a 20. This is a 10. This is a 1 and a 5. Okay, it's 20. Edge node. So this edge. Huh? What's happening? Why is that only printing one thing? That doesn't seem right. A 10 and a 20. We have a 1 and a 5. Oh, binarized DFS. This is tricky. Yeah, I killed this. Oh, I killed these edges. That's the problem. Okay, looks like we are correct now. I mean, technically, I don't need to get rid of these. Technically, I need to get rid of these. All right. Cool. Maybe I don't want to do that. This is kind of big. Wrong password? Seriously? Okay. Alright, I won't run in deeper, let's make it faster. How many test cases are there? Okay. This is kind of slow. Not a great finishing time. Okay, 6, but I think a couple people can still get ahead of us, namely Andrew, Mingda, and Kevin. Anyway, maybe I should do a little double checking before I declare victory. It's interesting that it doesn't complain until you do this. Yeah, I mean, I guess we can. In that case, is it? I think in this case it should not be upset. Yeah, okay, makes sense. Because then it's not initialized to complete undefined stuff. No, I actually want. Well, reverse. This. There's everything here. I don't know why I had a problem with the zip file. Okay, so we're in 6 now. Right now it is, I guess it's close to 140. 140 means that for some task means they'd have to be better than 130.43. So I think, yeah, anyway, like I said, these 3 are the ones that passed me. I think Kevin might already be too late. These 2 still can in a few minutes, with a few more minutes. Actually, Jahan can also pass. Anyway, enough of that. Let's, I guess, timer expired. So I can talk about the ideas for these problems. So I'll just go through these really quickly. Okay, cool. So problem A1, yeah, we've got the string made of f, o, and x. We want to know the minimum number of hand changes we need to type the string. We can type f and x with the left hand. We can type f and o with the right hand. So key idea here is that the f's don't actually matter at all. The only things that matter are the x's and o's, because those force us to change potentially. And first of all, if there's no x's and o's, the answer is 0. No change is necessary. If there's only one of x or o but not the other, the answer is also 0, because we can just pick the appropriate hand. And otherwise, it's just the number of x's and o's that basically the number of times we flip between x and o. So for example, in this string, the answer is 2 because the first flip occurs at this o. Notice before that it's all f and x. If we know the f's, then it's all x. So once we see this o, we flipped from x to o. We see another o, that's not a flip. And then we see this x, that is a flip from o to x, so that is 2. Similar logic gets you this one. This o is a flip, this x is a flip, o is a flip, x is a flip, and so on. And so A1 has really simple code. We're just going to loop through, see whenever there's a flip. If there is, then increment, and then output that. So linear time. Now A2, it is the same problem, but now you need to add up the answer for every substring of the string. So this turns out to not be too much harder if you think about it the right way. Basically, the idea is we're going to go through the string, and now whenever we see a character that flips, for example, let's say this O, basically we're going to count each substring with the same algorithm we used to count on A1. So if we do that, then we can ask ourselves a question: for this character, how many of the substrings will count this character? And that would be any substring that contains this character and also contains the previous thing that was different from it. So as long as it contains, the substring contains this x and this o, it will count this o. So basically we have 5 choices for the start of the substring here, and we have 7 choices for the end of the substring here. And so we just multiply 5 times 7. That is how many substrings count the O in the algorithm. So the idea is, if we're taking a substring and we're applying the algorithm, for example, this substring, I'll make this a little bigger. You know, we won't count this O, but we will count this X, we won't count this O. And this O is the one we're looking at right now. And the reason we count this O is because our substring contains this X before it, and it contains the O. So that's how we just count that. So we're just going to loop through, and then every time we run into that scenario, we're just multiplying the index of the previous opposite character plus 1 times n minus I. That is the number of choices of the start of the substring and the end of the substring, making sure that they contain both the current character and the previous character. All right, and now A3. A3 is this kind of messy problem where it's almost the same as A2, where you're building up a string, but now you have this new operation, period, which means that you are doubling the string. So you add the string to itself, you append the string to itself. And you need to simulate all these operations and then provide the answer for A2. The thing is that now the string can get really, really huge, so there's no way we can actually build a string. I mean, it can get 2 to the power of k in size, so there's no way we can handle that. So now we're just, it turns out we just need to save a certain amount of state. And it turns out in my case I have a couple different pieces of state. One is the index of the first x or o, the index of the last x or o, the value of the first and last x or o, whether it's x or o or whether it doesn't exist. Count, this is the count of x's or o's that differ from the previous x or o. N is the length of the string. Sum of P1 is, it's based on this A2 algorithm. It's the sum of previous plus 1 for every relevant x or o here. And then sum of Ni is the sum of this thing. Basically, we're trying to keep all these values up to date, where if we ran this algorithm on the string that we currently have, all of these values would reflect, for example, sum P1 would reflect the sum of this for the algorithm. And similarly for sum Ni. And then total is our answer. And then, yeah, the actual solution here just involves a lot of different calculations to keep all of these up to date. There's one case where we append a character to the end. This is a simpler case. Basically, if we think about how this sum of products changes, well, n just increased by 1 when you add a new character to the end. So we're actually adding sum of previous plus 1. That's why we add sum P1, for example. And then, all of these updates, similarly, it's just a matter of making sure everything gets taken care of, doing all these equations. It's a lot of, it's a lot of just messy equations to deal with. I actually had bugs for a long time before I finally got everything right. There's a bunch of different like if-else cases here to handle as well. So yeah, it's just a matter of really being careful with it and making sure all the states are updated. The way that I thought of these states is, I mean, obviously you start from, you want to update the total. What do we need to do that? And then you soon realize, okay, if we're adding a new character, we need to add the sum of the previous plus 1, so we need to track that too. And then, each of these, it's kind of like a bunch of dependencies. Total depends on sum P1. Sum P1 depends on last, so we need last. It also depends on n and count, so we need those. Total also depends on sum Ni, so we need that. And then, all these, you just kind of start with, okay, I want to calculate the total. You get all these dependencies, and then you end up with all the states, but luckily it is a complete state that, maintains itself. So just handle all these calculations, and then it is actually linear time. So the funny thing is that from A1 to A3, our solutions didn't get any slower in terms of time complexity, but they did get, higher in terms of code complexity. Okay, now let's talk about B. So problem B was kind of silly. It was actually the easiest problem in my opinion. Basically, you need to generate an n by m grid where every grid cell has a number, and you want to set it up so that if you find the path from top left to bottom right with the minimum sum, so for example, you could go here and then down, or you could go here and then right, or you could do some sort of zigzag, like here, 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 although that wouldn't be the minimum because you end up with a 2. If you take the minimum from top left to bottom right, it's a seconds, and if you take the sum is a, and if you take the minimum from top right to bottom left, the sum is b. And the squares have to be between 1 and 1,000 inclusive. So just basically you're given n, m, and a and b, and you want to generate this grid or determine that it's impossible. And this turns out to be super simple. First of all, since it has to be at least 1, the minimum value for a and b is n plus m minus 1, because that would be the cost of just taking any straight path, or any path, straight down and right that only involves ones, or vice versa, top right to bottom left. So the code looks like this. If either one is less than n plus m plus 1, n plus m minus 1, it's impossible. Otherwise it's possible. And then what I do is actually really dumb. It's just you can kind of see this for this example. Oh wait. Or maybe even an even better example is 5 by 5. Let's do like 100 and 100. I just make everything ones, and then I make these two values big enough so that the path here and the path here adds up to 100, or whatever this number is. So the only, yeah, I just make a grid of 1s, and the only values I change are the top left and the top right, and then I output that. So actually a really simple problem. Kind of weird that they set it up as B. I feel like this could have been A easily. But anyway, yeah, this is definitely, I definitely think this is easier than A1 and A2, even though it's worth more points. Okay, anyway, and last problem is C. I guess we can check the scoreboard in the meantime. I wonder if I dropped it all. No, it looks like I'm still 6th. So yeah, I think that means as long as I pass everything, I should be a confirmed 6th place, because nobody can pass my penalty at this point. Yeah, because it'd be almost adding 2 hours, and nobody's within close to 2 hours of me. Okay, anyway, so problem C. Yeah, we've got a tree. The tree has weighted edges. The weights are between 1 and 20. And we're defining the shipping capacity between a pair of nodes as the minimum capacity of any road on the path between them. And now what we actually want to know is if we remove, for each road, if we remove that road, what happens to the total sum of shipping capacity across every pair. And if we remove a road, then the shipping capacity between pairs that are disconnected becomes 0. So that's basically what we want to do. In this case, for example, for this tree, the shipping capacity between 2 and 4 is going to be 5, because it's the minimum of 10 and 5. Between 2 and 3, it'll be 1, because it's just the minimum of 10 and 1. Between 2 and 1, it'll be 10. And so, for example, if you were to delete this edge right here, then the total shipping pair capacity would be 1 and 4 would be 5, 1 and 3 would be 1, and then 3 and 4 would be 1 as well. So 5 plus 1 plus 1 is 7, and 2 can't reach anywhere else. So 2 doesn't contribute to the total. So we want to know these answers for every edge, what happens if you remove it, and then they ask you for the product of all the answers. The reason is just they want to limit the amount of output. But really we need to calculate the answer for every edge. Okay, so it is helpful that the capacities are only up to 20. That helps make it a problem where we can just, basically we can just iterate through kind of each of the capacities. But the way that I solved this was centroid decomposition. So the idea is that when you have a certain centroid, you can kind of take care of all the pairs that go across that centroid. In my case, I did an edge version of centroid decomposition, and so you have a key edge, and then you want to take care of all pairs kind of crossing that edge. And so we're just going to update. It does two things at the same time. It calculates the answer for the entire tree without removing any edges, and then it calculates how much you lose from each edge by removing it. And we do this by computing like a frequency table for each kind of subtree. So we take an edge, and we take the two subtrees formed if you cut that edge, and then we sort of just DFS those two subtrees. And then for each node, we're computing for its subtree the frequency of how many times is the min weight from the root edge down to here equal to C. We compute those frequency tables, and then what we can do is, if we have two subtrees that we want to take all pairs between, we just use the frequency tables to compute that, and it's just some simple math. It actually ends up, it just takes 20 iterations and you can compute that. But yeah, basically, I'm not gonna go into too many details here, but basically centroid decomposition, take the crossing pairs, and then for each edge, we're gonna subtract its subtree crossing with the other half of the tree. And that way, and then we just continue recursing. That way we solve both the sum for the entire tree and the amount that we lose for each edge. And so once we do that, we have the entire tree subtract the amount we lose for each edge, and then just multiply it all together, and that is our answer. Yeah, so just brief explanation, not too into the details. Feel free to check out the code if you want more details, but yeah, that's it for me for this contest. We'll see how the system tests end up, but I will see you in the next one.